really weird to me because it's daylight in the windows and stuff, so I'm feeling a little bit discombobulated here. Before we get started tonight, I have a couple of announcements I'd like to make about other events that are coming up. I'm still working on our next Spaceport lecture for April or maybe even May. I'm working with someone who's may or may not be able to make it, and we'll see how that works out. Of course, we finally got Arturo here, and Arturo being Arturo, he's out there just chatting away. But anyway, so I always like to thank Arturo Machuca and the Houston Airport Systems for their sponsorship of the lectures. I won't bore you with the movie, but things are cooking, and he'll hopefully be able to give an announcement next time. Oh, and I've got this, which isn't working because I turned it off. You can do this. Now, the reason I'm bringing this up again is the Twitter feed. That's going to be important in a second. So I know most of you probably don't tweet or Twitter or whatever it is you do. But it's a good way of communicating. I get a lot of my news from Twitter. Some I don't want, but I get some of it that way. And the reason is I'm making this announcement tonight. This isn't actually officially online yet, but many of you might know that the September 12 is the 55th anniversary of President Kennedy's To the Moon speech at Rice Stadium. And so to commemorate that, we're planning a series of events, some which we hope will start when I get this website up. Treasure and David are helping me with that. And we are going to do a number of different things in partnership with NASA, Johnson Space Center, and with Houston Independent School District. The first one might be of interest to some of you. It's called the storyboard. That will be the first thing we do, which again I hope will come up soon. And what we're looking for is stories, short 350-word stories or less, of inspirational stories that anybody who was at the speech or had grandparents or parents or great-grandparents at the speech or something that allowed them to take that message, which is a very forward-looking message, and inspire them in their career choices or in something that they did. We're trying to collect a bunch of those stories as a kind of nice commemoration of it. We're going to do a Twitter competition. I won't tell you more about that, but we're going to use the hashtag #BoldFrontiers. And the reason that it's called Bold Frontiers is because the last 4 words of Kennedy's speech was "We must be bold," and I think that applies today too. We'll have a special lecture, I hope, on September 12th. And for the high schools, middle schools, and elementary schools, we're doing a mission patch competition where they have to design a mission patch that commemorates Houston's involvement with the space exploration and the theme of being bold. And we'll have some nice prizes for that. That will probably not start until September because the summer's in the way of the schools really taking part. And then we'll have a number of other things that will go on. So sometime in the next couple of weeks, all of you, I think, are signed up for our lecture notification, which is why you're here, in part. If you're not, please sign up for that, and we'll just let you know about these activities as we go. If you've got a nice story that you'd like to tell, please feel free to put that up on the website, and you'll see these things develop, particularly starting in September and going through until the end of the academic year in 2018. Keep forgetting I've got this. A little bit of self-promotion here. There's a couple of talks coming up. The Sigma Psi Honor Society Awards Banquet is on April 20th. They've asked me to be their keynote, and I'll be talking about the space exploration hazards of living with a star. Some of you have heard some of this before if you've heard me talk. There'll be a little bit of stuff that we'll hear much better tonight than you'll hear from me, from our speaker, and then feeding that into some of how it affects some of the new commercial space activities. Unfortunately, this will be over in the BRC. It costs money, so some people might think I'm worth it, most people won't, but if you're interested, you're welcome to be part of that. And then another bit of self-promotion is part of the Moody Center for the Arts. I don't know if many of you have visited it yet. It's a fantastic new facility we have. It's open to the community. It's a whole bunch of really interesting things going on there. And one of the events they have an exhibit right now called the Starry Messenger, Sidereus Nuncius, for those of you who like Galileo. By, I think she's Californian, artist Diana Theater, and we're going to have a little panel discussion on the day after, so the Friday, April 21st, over in the Moody Center. I believe that's free, so it'll be worth the money. I'm sure Diana's very interesting. So we'll have a little talk, and it's to do with, she's done a lot of really interesting filming at the Hayden Planetarium, so it should be kind of fun. Now, the reason we're here, this is great for me because when I first came to Rice, one of the first people I hired, because I really needed somebody good to help me get started here at Rice, was tonight's speaker. And I think we were very successful. I'm really proud to say that we did a lot of good things. And then, of course, she said, to hell with this, and went off and did a lot of better things. But Holly came to us from the High Altitude Observatory, where she was, she'd built up quite a reputation as a very, very solid and fantastic scientist. She brought a capability here that we didn't have, and I think we've had a number of students benefit from that. A couple, at least one is here tonight. And so it's just great to, she's so busy nowadays, I hardly get to see her, so it's great that she's back. And I'm really looking forward to tonight. But since I hired her, since she was at Rice, the resume's got a lot more padded here. It's got a lot of good things on it. So Holly she's the director of the Heliophysics Science Division at NASA's Goddard Space Flight Center. Heliophysics is a word you'll hear a lot tonight. It kind of encompasses solar physics, which is what we do, but its effect on planetary systems and in the heliosphere and so on. And so we'll hear more about that. And she's also is the NASA Deputy Project Scientist for the Solar Orbiter mission, which I presume we're going to hear about, a European mission with US participation. Her expertise is in erupting prominences and filaments and coronal mass ejections and solar variability and activity. And so she joined, we were just amazed that she left Rice almost 9 years ago, which is astounding to me. But since joining Goddard in 2008, she's been the Associate Director for Science, Chief of the Solar Physics Laboratory, and Deputy Director for the Solar Physics Laboratory, I think, if I'm reading that right. She got a BS in Physics from the University of Colorado Boulder, and her PhD in Theoretical Astrophysics from the University of Oslo, Norway, which are in the news a lot today because of IRIS and some of the missions there. Great school. Prior to joining NASA, she was a research scientist here and associate scientist at the High Altitude Observatory in Boulder, Colorado, as part of the National Center for Atmospheric Research. She's received the Women in Aerospace Awareness Award, the 2015 AGU Athelstan Spillhouse Award, which is both very prestigious awards, many NASA honors, and she's even had a solar telescope at the St. George Observatory in Shreveport, Louisiana, named after her. And for her sins, she is currently the Vice Chair of the Solar Physics Division of the American Astronomical Society, as a prelude to becoming the Chair of the SPD next year, where she has to work less. Yeah. So please join me in welcoming Holly Gilbert.
Thank you so much for that. Oh, that'd be great if you could dim the lights. I'm absolutely thrilled to be back here. I can't believe I haven't been here since I left, which is very strange. It seems like just a couple of years ago, and I was talking to somebody earlier where my sense of time is just off. Either things feel like they've been years and years, or they feel like they've just happened. So I don't know what happened. Age is causing some strange time warp. Oh yeah, that's right. So we've had this. Everybody is telling me I should switch to a Mac, and I've been meaning to. It just hasn't happened yet. I know. Okay, maybe by next time I come give a lecture, I'll have switched. So the title of the talk is Probing the Solar Corona, and I'm going to talk about the corona tonight because I think it's one of the most interesting, coolest, actually hottest places in the solar system that we haven't explored yet. Working at NASA, I get exposed to all kinds of really neat missions. We're going to Mars, we're going pretty much everywhere else in the solar system. And yet the sun is a very difficult place to study because you cannot take missions and land them on the sun. So as much as I love my colleagues that study Mars and the other planets, and I think this is an area hopefully that I can get you to be excited about, because we have a couple missions coming up that will be fairly close to study the solar corona. Now, my obsession with the sun is nothing new. Throughout history, humans have, of course, been obsessed with the sun. We know a little bit more now than they did in the history, but it's always been this fascinating object in the sky. And for a long time, people didn't understand exactly what it was. 1860, there was a drawing of an eclipse. So they knew about the solar corona for a long time because of solar eclipses. The corona can only be visible if you block out the very, very bright disk of the sun, like the moon does in a total solar eclipse, or if you have the right equipment to study it in the correct wavelengths outside the Earth's atmosphere. So I'll show you some of that. But what's interesting in this picture, or this drawing, is that there is a bubble coming out of the sun, and that's actually a coronal mass ejection. Is there one? There we go. So this is very telling and very interesting. Nowadays, these are the people that are obsessed with the sun. We are people that gather in international conferences to study the sun, basically. We also have conferences where we have dinners together, and I think you'll recognize a couple of people from Shine in this. So, I mean, we have an entire community that studies not just the sun, but as David mentioned, how the sun affects us here at the Earth throughout the solar system at other planets, and that's called heliophysics. Oh, did you want to take a picture of that? Okay, good. Oh, yes. But nowadays, this is how we observe the sun. This is the Solar Dynamics Observatory. It's an artist's conception here. This launched in 2011, and it has its eye on the sun all the time in a variety of wavelengths that allow us to see the outer corona. Well, the corona is the outer layer of the solar atmosphere. And again, it's very difficult to study and to image because the solar disk is so bright. So we have to use these various techniques to study it. And SDO, or Solar Dynamics Observatory, is one fantastic mission that has been allowing us to do that for years now. The amount of data coming out of this mission is incredible. It's a terabyte a day. So it's a lot of data. It's necessary to understand what's going on in the sun. Now, why is that? Okay, well, the sun is this tranquil thing in the sky, right? Well, no, actually, it's extremely dynamic. You can see from these movies, a lot is happening on the sun, a lot of very violent behavior. This is why we need to study it more. This is the stuff that can impact us here at the Earth. Let me just this is not a comprehensive list, but what we do know now are some fundamental things about the solar corona that we didn't know even 100, 200 years ago. So the atmosphere, like I said, the solar corona is the outer layer of the atmosphere. It has different layers. It is not symmetric. It's actually highly structured, and it's driven by magnetic fields. So it's this interesting area that's dominated by magnetic fields and hot plasma. And what's really interesting is that it's very, very hot. The corona, which is furthest away from the core where energy is being produced inside the sun, is hotter than the surface, which is very weird. You think the further away you get from the source of the heat or the energy, the cooler it will get. So that's one thing that we study. We know that the sun is constantly blowing out its outer atmosphere. So there's a thing called the solar wind, and it's not like the wind here on Earth exactly, but there's a constant stream of particles blowing away from the solar sun, and we're embedded in that. We actually live within this outer atmosphere of the sun. And to make things even more complicated, the sun has what we call an 11-year solar cycle activity cycle, and that is basically the sun is very, very active, and then it goes through a time where it's not very active, and it doesn't have very many sunspots. Sunspots are related to activity. And then it goes back up, and it gets back to solar maximum, where it's very, very active again. And this happens on average about 11 years, where it goes from maximum to maximum. Now that changes. Sometimes we've had solar minima or solar cycles that have lasted 14 years. So that's just an average, but that's something that we know now. And then coronal mass ejections, like that drawing, that bubble, we know that those happen. We also know that there are other large ejections and things that happen on the sun, like in the movies that I just showed. Okay, so that's pretty impressive. We know some stuff. here's an example, drawing of, or an animation of what happens in the sun. Magnetic fields are generated in a layer that's about right here. So they're generated, they come, they get stressed, they poke out through the surface, and they rise. And the reason I'm showing you this is because this is really the cause of space weather and the cause of these solar storms, as you can see in this animation. That's not real data there. This is real data, however, and that is a picture of the magnetic field. So there's a positive and a negative, and you can see the white and the black pepper showing you where those two polarities are across the sun. Okay, so keep that in mind as we're moving forward. These are images of the corona and describing different types of dynamic phenomena. So we have solar flares, which I'm sure everybody has probably heard of or seen. We have the coronal mass ejections, these big, large bubbles blowing away from the sun, extremely high speeds, very energetic. We have other things that are happening in what we call the quiet kind of sun, stuff going on everywhere. We have coronal jets. So the corona is this wonderful place of activity that allows people like me who are interested in when it's active to study. Some people like it when it's quiet because they study certain other things, but it's been really, really quiet lately. We're on our way down to solar minimum, and it's been unusually quiet. I think it's been 15 days straight without a single sunspot. I think that's right. So, oh, good. So there are some storms coming our way. Too bad we're at low latitudes. We can't see the aurora if they hit. And I'll talk a little bit more about that, actually. Okay, again, this is not a comprehensive list because there's a lot more that we don't know, but just to give you an idea how much we don't actually understand fully. We do not know why the corona is so hot. We know that it's structured and we know that it's hot, but why in the world is it so much hotter? It's on the order of it's like 1,000,000+ degrees. The surface is about 10,000 degrees. So it's 2 orders of magnitude hotter than the surface. Very strange. We do not fully understand how the solar wind is accelerated. We know that there is a solar wind. We know that it's accelerated, but we do not understand how. We do not know why that 11-year cycle occurs. There's something going on in the sun, the solar dynamo, that's causing this cycle, but why 11 years? So we have a lot of people working on that problem as well. And then also those large ejections, coronal mass ejections, how exactly are those caused? Okay, so some pretty interesting questions to study. Why should you guys care? I care because it's intrinsically interesting to me, and I can't imagine everybody wouldn't be so interested, but there are practical applications for this activity that happens on the sun. And here's just a picture of aurora, since we're not going to be able to see it tonight. Yeah, it's funny, I saw the aurora for the first time a couple, 2 years ago, 3 years ago, and it's amazing. So. Let's see here. Okay, again, let's look more closely at these extremely dynamic phenomena. These are the coronal mass ejections, and you're looking at what we call a coronagraph, which is it's a fake eclipse with this black disk blocking out the very bright sun. Now we've put the bright sun and imaging right back on top of it to show you the connection of these bubbles coming out and how they connect to the surface. You can't see it from there, but it helps us determine where these things are coming from. So you've had these large bubbles blowing out extremely fast speeds sometimes, carrying a ton of mass. I mean, it's a lot of hot plasma blowing out, a lot of magnetic field. And the reason that we care is when they're directed at the Earth, this is the animation David showed. This is actually a model simulation of what would happen to the Earth's magnetic field. This is the Earth in a nice sort of somewhat simple magnetic field compared to the sun. And you can see that the sun is, of course, over on that side. And one of these coronal mass ejections hits the Earth. Sorry, I keep going into that. I get less excited about this. Yeah. Special sound effects, right? And you can see that the Earth's magnetic field gets completely changed, and it gets compressed. It gets kind of stripped away because there's an interaction with the magnetic field from the coronal mass ejection with the Earth's magnetic field. So it basically strips that magnetic field that is facing the Earth away. And so this is very important for space weather effects. And I'll talk about those in a bit. This is an animation of what's happening around the Earth. So when these things hit, they're dumping a ton of energy into the Earth's magnetic field. which then goes into the atmosphere. And these are what we call the radiation belts. This is just an animation. This is not real data. But this is to show you kind of how that energy changes. And red symbolizes high density of very high energy, high energetic electrons. So these things come into the magnetic field of the Earth. They get trapped in what we call these radiation belts. And this is an area where satellites will have a hard time flying because of this extra radiation and this energy. So I've already mentioned a couple of space weather effects, but again, the reason that we all care, and NASA specifically, there are a couple of effects that happen when all of this energy gets dumped into the magnetosphere and the magnetosphere changes and it breathes. And one of those issues that NASA is very concerned about is that it causes satellites that are sitting in a particular orbit to sometimes fall down, or at least to lower orbits. And that's because they're sitting in a layer of density that's a certain density. When solar storms occur, they can cause that ionosphere to change, and it actually expands. And so all of a sudden, it can expand and decrease, and so the density is changing. And the orbits have to be changed. You have to either thrust to keep up with the changing density, or they can fall down. And so that's one reason we need to be able to forecast and say, look, there is a solar storm that's headed our way. We have to be careful, and it could cause a problem with the ionosphere. And actually, solar flares that occur at the sun are especially problematic for this. I just showed you some of the radiation belts. This is, again, we want to be careful. This is a GPS satellite. If it goes through these radiation belts, that can cause problems when they're very energized or when there's a lot of these high energetic electrons. It can cause blackouts. Now that's more applicable to folks here on the surface of the Earth, where we're protected from the Earth's atmosphere and the Earth's magnetic field, but currents can be driven from all of these high energetic particles blowing into the Earth's atmosphere, and that can induce currents. Well, it is actually inducing currents up there, and that can also cause problems with ground. And so blackouts happen. In 1989, there was a large blackout in North America and Canada. And so this has happened. We know that this does happen, and it's important, again, to predict and to try to forecast this so we can take precautions. Okay. Well, so we have these issues. I showed you kind of what we know, what we don't know. We still have a lot to learn. It's job security in a way for me, but it'd be nice to be able to really predict space weather. When are these storms going to happen? How are they going to impact us? Just because a storm, what I'm calling a storm, coronal mass ejection, like with a flare, just because they occur and they happen to be directed at the Earth does not mean that they're going to cause problems. So it's just not quite that simple. It depends on the magnetic field orientation. It depends on a lot of other things. So modeling these things is tough. But I'm claiming that the way we make progress and what we've been doing is we observe. NASA satellites, ground observations, we observe and observe more. We need a lot of observations. But we then use those observations to kind of see what's going on. We need to model some of that activity. And then that model helps us feed back into looking back at the observations. Okay, so the observations help inform the models, and the models help us learn more about what we should be looking at. And it's kind of what I think about this kind of cycle. My husband disagrees. He's like, that's not progress if you're repeating. I'm like, well, if you keep informing the models, then yeah, we're making progress. Sorry, I called you that. I just like to tell you you're wrong in front of a large group of people. So these are the types of observations that the Solar Dynamics Observatory takes, and we're looking in 3 different wavelengths, which actually kind of means we're looking at 3 different temperatures, and these are very hot temperatures. So you're really looking at the solar corona, which you can't do from the ground or when you're looking at it because we don't see these wavelengths with our eyes. So we have to have satellites above the Earth's atmosphere to view the corona in these wavelengths, and you can see that there's a lot of structure there. These loops are the magnetic field lines, and we're able to see them because the hot plasma gets trapped on them. So this is a very important way of observing what's going on in the corona, and we have to have multiple wavelengths. The solar atmosphere is very structured and different depending on what wavelength you're looking at. To get a full picture of what's going on, you really need to look at several wavelengths. And that's just an example there. Now, there's some very cool things that happen. Yes, it's a composite, so they're all put together, yeah, yep. But you could kind of see how they were even a little bit different. And the cooler lines look much different. Actually, this is a cooler line here. This is about 100,000 degrees. The other ones were a million and a half degrees, Kelvin, sorry. And this is interesting because as David mentioned, my area of expertise is looking at these erupting structures called prominences, and that's exactly what we're seeing here. It's a dark structure, and it's dark because it's very cool relative to the corona, and it's absorbing that radiation. And so it appears dark until sometimes it erupts, it gets light because it's then heated. But this is an amazing kind of phenomena that we kind of understand. We don't even know exactly why these things form. So there are these things on the sun hanging out in the solar corona, and they're so dense and cool relative to the corona that it's very interesting that they can actually be suspended up in the corona. And when they erupt, it's even more interesting. You can see kind of that very interesting structure there. And that's basically outlining some of the magnetic structure that's holding that plasma. Let's zoom out a little bit. Not a little bit, a lot. Here's again one of those big coronal mass ejections. And in this one, you can see how it connects to the activity happening here. And you can see, for those of you who have good eyesight, there's kind of a wave that goes off here. And so what we're good at now is connecting these large coronal mass ejections in the white light data, where you can see it with your eyes like you can in a total solar eclipse, down to the surface where things are happening. That's where things are being generated and caused. So it's important to be able to look all the way down. Okay, this is one of the big problems in solar physics, is this eruption initiation. Sure, they're happening. What is causing them? Well, we know the basic fundamental problem is that magnetic field lines are interacting, and they're causing what we call magnetic reconnection. And that causes explosive things like flares and magnetic fields to then go away from the sun. But there's a lot we do not understand about how they're happening, why they happen. Now, we do know where they will occur in a way. And I say sort of because we know that they occur during these, along these filament or the prominence lines where they sit. We know that they occur near sunspots. But again, not all of these areas are going to cause a coronal mass ejection or an eruption. So you can have sunspots that don't cause any eruptions. So we know sometimes where they occur, but we don't know enough about that. So again, we don't know when this will happen. We also don't know how strong they will be. Some eruptions are very, very minor and very, very small. And like I said earlier, we don't even know how much, even the strong ones that hit the Earth, we're not really sure how disruptive that will be to the Earth. So we must understand this initiation mechanism to answer these questions. That is very crucial. And at NASA Goddard, we're looking at models and we're looking at observations to try to solve this problem. Now, I'm going to claim that this really is the holy grail of space weather prediction, and that's coming from a solar physicist point of view. Because there's some geospace people that would say, well, not really. It's how you can tell what's happening at the Earth. That's more important. But if we were able to fully understand these things, then we could predict. We could say, look, this region on the sun we know is going to produce this type of flare, this type of eruption. It's going to be extremely powerful. It's going to hit the Earth. If we knew all that, we could really lead to prediction in space weather. That's our goal. Now here's some example of some modeling. These lines represent the magnetic field lines, and this is the sun here. You can see this weird stuff happening. So these magnetic field lines interacted. Here they are doing this again. They come together and they change structure. And even though you can't really destroy magnetic fields, they do this weird thing at the microscopic level called magnetic reconnection. And you can see there's stuff flowing back down. That's energetic particles causing solar flares. And we have some experts in the audience that study these things. And you can see all kinds of material flowing outward. Now again, this is a model, but this helps us understand some of the fine structure. And if you zoom out, I could not get this movie to work, but you can see the complication here, some strange islands of material. And this is a very simple picture. I mean, magnetic fields are not just, this simple. This is very, very simple picture. But even with a simple picture, it's complicated to understand how they all work. Now, I'm going to show you this event because this is a very, very powerful coronal mass ejection solar storm that occurred and hit one of our hit one of our missions called Stereo A. So we have two identical spacecraft that have been circling around the sun to look at the backside of the sun because we can't study that from the Earth, and that's really important to understand some of this. And so these have been going around the sun, and there was a huge, huge storm that hit Stereo A. Luckily, it was far enough away that it didn't hit the Earth. But had it hit the Earth, it would have caused a lot of problems, at least we think. It can cause a lot of, the damage that it causes is to satellites, to the power grids, and that can cost a lot of money to repair. And the more technologically advanced and dependent we are, the worse these things can be. So this is an interesting, we dodged a bullet on this one. Of course, probably some of you know about the huge event in 1859, the Carrington event, and that was the largest event that we know of. We don't know when the next large event will happen. It may not be in our lifetime, or it may be soon. So again, just the importance of knowing more about this. This is a model of that event. Actually, I'm going to have to exit out of this because this is important. I'm going to take the chance here. This event is modeled by what we call an Enlil model. Okay. So let me just do this for a second. I apologize. Let me get this bigger. Okay. Let's play this here. It's hard to do without glasses. Okay. So I want you to look. So this is the sun, very small. The Earth is right here, so you can see a coronal mass ejection. This is a model of density, and we're looking at the ecliptic. So we're looking down at the solar system, basically. And so one of these mass ejections comes out, hits the Earth. There's a couple of other things going on here. Here's Stereo A. This is the spacecraft that's going to get hit by this huge event. Now, in here, this is density. So the higher the density, the redder it's going to be. Here, there it is. That's that huge event. Missed the Earth, but look how massive that is. By the way, this is Jupiter out here. These things travel throughout the entire solar system. They affect our satellites at different planets. So NASA does forecasting for space weather to protect our NASA satellites at Earth and also at other planets. Oh, that's not going to work now. Okay. Let me go back to full. Let's see if I can do this. Okay. Okay, here's just to show you. Okay, this is a more zoomed in. Jupiter's way off, but this gives you a little bit better idea. This is not that same event, but it's kind of a good example of what's happening. So here's the Earth. Here's some of the other planets. Of course, not to scale, but you can see, you can get the idea of this blowing out. Here's a side view as it is hitting the Earth. So this is not looking from the top, but from the side. Okay, enough of the modeling. Now, NASA is on this, right? We have 18 operating satellites to look at what's happening on the sun, how it's impacting us here at Earth, and actually all the way out through the heliosphere, the domain of the sun. And these are examples of those missions in orbit. So we have them orbiting in different types of orbits, and it's crucial to have, you may be asking, why do you need so many? But there are so many different aspects of this system, what I'm calling the Sun-Earth system. Again, I showed you images from the sun, but that's only one piece of it. We need to understand how it's coming towards us, what it's doing in the middle of those 93 million miles, right? A lot can happen, especially because the sun is rotating, and you saw those spirals. Those are the magnetic field lines getting dragged along. Not just a simple, straight path necessarily to the Earth. So here we are. This is the heliosphere, is the domain of the Earth. So I'm sorry, of the sun. So this is kind of a neat thing to kind of just capture the importance of observing all that. Now, we're going to add a couple more missions to that portfolio. Very exciting. Solar Pro Plus is a mission that is basically going closer to the sun than we've ever been before. This is an idea. This is how close it's going to be. So this is an eclipse image. And again, you can see the nice corona, the nice structure. And this is how close Solar Probe Plus is going to get. It's going to be within 4 million miles. Now that sounds like a kind of a long ways away. Just remember, 93 million miles is the distance from the sun to the Earth. So it's within a very close region. This is important because it's going to be able to take in situ data. It's going to take observations and sample the coronal material inside, closer to the corona and to the surface than ever before. And this is important because this is where solar wind gets accelerated. Remember some of the things that I told you we don't know? This will help answer those questions. Just a few more facts about it. It's getting very close to the sun, so it's exposed to a lot more energy, right, than we have at Earth, about 500 times more. It has to deal with 2,500 degrees. It's going to be launching in July of 2018, coming right up. And it's cool because it uses seven gravity assists around Venus. Here are the science objectives. I sort of touched on one or two of them. But again, we need to get that close to sample the actual corona. And this is going to help us do that. The plasma near the surface or closer to the corona, inside the corona, is different than it is near the Earth. There's another mission that's going to go relatively close to the sun, and this is the one that I'm involved with, the Solar Orbiter mission. And David mentioned this is a collaboration between ESA and NASA. NASA is providing 2 of 10 instruments and the launch vehicle. Now, this was also supposed to launch in 2018 in October. Until about last week, it got slipped officially till February of 2019, but that's okay. That's not that bad of a slip. It's very interesting being involved in a collaboration with another space agency. They do their reviews differently than NASA does, and it's very complicated. It's been interesting to watch how the logistics and the politics work. Let me just tell you a few things about Solar Orbiter. So this has somewhat similar science objectives, but not quite. So how is the sun creating and controlling its domain? Why does solar activity change with time? Again, that 11-year solar cycle. What drives the solar wind? Where does the solar magnetic field originate inside the corona? How does it vary? How does solar eruption? So again, these are kind of things I've been talking about that hopefully Solar Orbiter will help us answer. Now here is just an image of some of the orbits. The cool thing about Solar Orbiter, okay, Solar Probe Plus is going to go really, really close to the sun. Solar Orbiter is also going to go relatively close within Mercury's orbit, but it is going to kick out of the ecliptic, and that's very good because we're not able to image the poles of the sun, and that's where a lot of stuff happens, and it gives us a better idea of the global magnetic field of the sun. So this is very exciting. It's kind of hard to see, but this is the one that's out of the ecliptic, and this is going to take. The mission is going to be 7 years nominally with a 3-year extended mission. So we're hoping to fly that for quite a while. This is cool because this is the heat shield. Of course, it also needs a very protective heat shield. I should have mentioned the Solar Probe Plus heat shield is 4.5 inches thick, and it's a carbon composite, so it's very neat. This is the size of the one that's about to get tested for Solar Orbiter. This is a while ago, and it's being dumped into I think it's a thermal vacuum. But you can see the size of it relative to these people. And this is the temperature, the thermal profile. So you can see that the heat shield, which is facing the sun, of course, blocking all these instruments behind it, is very hot. It's not as hot as Solar Probe Plus, but it's still very hot, 500 degrees Celsius. Now, what's interesting is it's strange that the instruments behind it, just directly behind it, are actually more like room temperature. So it does a very good job of protecting those instruments. I was telling somebody earlier, we have to deal with scattered light from different objects, and so different thermal things. So it's a very complicated thing to do, to work. Very, very good engineering, but we're able to do it. And so this is this might make some of you a little dizzy. This is what Solar Orbiter is going to see as it launches. Okay, so it's going to go. So if you're going to get sick, because I get motion sick easily, don't watch, but it kind of gives you an idea as it's going out of the ecliptic too. This is really long. This might take a little while. But you can see as it's getting closer, and then here's like the polar region. Oh, yeah. And you can see how it's shifting. I wonder if I can speed this up a little bit, because it does this for a long time, just to show you where it gets to the polar region. Okay, so now we're getting closer to it's 7 years. Yeah. Now, the reason I'm showing this is because I think it's really cool. Once we see there's the North Pole, and then it spins around, and there's the South Pole. And so it's this ecliptical orbit, but now at this point, it's about 30 degrees out of the ecliptic. And again, it's very exciting for solar physicists because we've never been able to study the polar regions before. Now, the orbits of the two missions, they're synergistic. They're going to help each other study the major problems in solar physics, and not just solar physics, but heliophysics in general. And this is an animation of the two missions if they were to have launched on time. Even this is a few years ago. Originally, Solar Orbiter was going to launch in 2017, so this is a little old, but it's not going to be exactly the same because our launch slips. But to give you an idea of the different orbits, and if you can see, difficult to see. So there's Solar Orbiter orbiting around here in its elliptical orbit. Pretty soon, there's Solar Pro Plus. So that's also an elliptical orbit, but it's going closer to the sun than Orbiter. And they're going to be aligned at certain times for very interesting scientific studies. Every once in a while, they're going to be aligned with the sun. So we'll have Solar Pro Plus close to the sun, Solar Orbiter further from the sun, and then the Earth. And that gives us a direct line of plasma, studying the plasma. Solar Orbiter also has in situ measurements of the plasma, the hot gas, but it also has remote sensing instruments. So not only can Solar Orbiter provide a link to the closer mission to the sun, but it can also provide the background imaging data. Sometimes they'll be aligned at 90 degrees to each other, and that's also useful because if Solar Probe is sampling a coronal mass ejection coming away from the sun, and it's taking the data right there, Solar Orbiter is able to show exactly what's happening from the side and how fast it's going, and so it's additional information that together will be very, very useful. This is just a screenshot of just for those of you that don't like the circling. So this is late in the mission. So Solar Pro Plus, highly elliptical, very close to the sun. Solar Orbiter out of the ecliptic. It's always kind of hard to tell which is out of the ecliptic, but again, that's kind of a way to. Okay, now, again, NASA is important. Having instrumentation out in space, extremely important for this. But one of the best ways to study the solar corona, at least the inner solar corona, is through a total solar eclipse, a natural total solar eclipse. And that is because it allows us to see all the way down, almost to the surface, like really close down. And the moon is just a wonderful coronagraph. It happens to be the right distance and the right size to just block out the disk of the sun, providing this beautiful view of the solar corona. You can see very, very fine structures. This is just amazing. So unfortunately, these only last for a few minutes, and they only happen every 18 months or whatever. So it's not ideal for using for science, but we can get some very good science out of this. Now, the reason I'm bringing this up is because on August 21st of this year, there's going to be a total solar eclipse in the United States. And it's going from coast to coast. And so hopefully all of you know about it, but if you don't, I'm going to show you. I highly recommend you see this, even if you have seen a total solar eclipse, but if you haven't, you're going to be absolutely amazed. I've seen one, and I was just, I couldn't believe how amazed I was. I was amazed at how amazed I was because here I study the sun, and yet it was like a religious experience. Here I am, watching the solar eclipse. So Pat Rife was telling us, one thing you want to do if you do see a total solar eclipse, don't take the video and the pictures of the eclipse itself. Set it up so it's taking a video of your reaction, because that's really neat to have documented. I just watched the eclipse. My husband was taking pictures. Again, doesn't listen to me. So here are some of the cool scientific things that you can get from eclipses. And again, because one reason is that we're so far down in terms of the corona, but we have techniques that allow us to get density measurements, which we can get that from coronagraphs and white light. But we have techniques that we can get temperature differences along the corona structures and velocity. And this, again, is important if we're studying this dynamic behavior or even just regular behavior. So eclipses are very cool, and they still provide us with some important science. Now here is the path of the total solar eclipse, August 21st. So I'm going to be here, because I'm running the SPD. I'll be in Portland for the SPD. Salem is right in the path, so we're going to be in Salem and hope that there's no clouds. Yeah, that's a really good place. Wyoming is definitely a good place. You know, there are no guarantees. You may travel somewhere to go see it and get clouded out, but if you see, it's worth it if you have a chance to see it. So if you can't make it up there, I mean, there's a lot of places. I would recommend making plans now. A lot of places in the path, the cities in the path, or hotels are already sold out. Yeah. So NASA is also going to be helping in terms of looking at the shadow on the Earth, and which is neat. It's kind of funny because since I've made this slide, this one here, Discover, is on the president's budget to not be taking Earth-looking images anymore. So that might not be the case. But if it is up and running, then it will show us the shadow, the overall larger shadow of the eclipse going across the country. Sorry, I did not know that had audio. No. Well, we can. We can turn it off, I guess. My mute is on here. I thought it was. Okay. I'm scared. Yeah, sorry. It's a movie of the Aurora, so it's okay. We don't have to do this. This is the last slide. But again, the Aurora is a beautiful natural consequence of space weather. So it's not all bad, but it's a beautiful thing to see if you can see the Aurora as well. Two best things in the world to see, in my opinion: the Aurora and total solar eclipses. So that's all I had. So thanks for listening. Appreciate it. Thank you for reminding me. So, since I've convinced everybody they need to see a total solar eclipse, we have eclipse viewing glasses for anybody that would like some. So please grab them, and be careful when you look at the eclipse. Make sure you.
We'll put them near the back, so I think there's plenty for everyone to take one. So please don't grab a handful, but or maybe we just hand them out. And this is courtesy of Pat Rife.
Yes, Pat Rife.
So this is Professor Rife.
There's a website listed on there. That's her website, and that also links to the NASA website in case you can see all the activities. We're doing a lot of outreach with NASA, so good information. All right,
the floor is now yours. So.
I was just curious about the event that happened in the 1800s. How do we know that event if we didn't have the accurate scientific equipment at that time?
Right, very good question. Well, we know it was extremely strong because of the effects it had here on the Earth. So the technology of the day, telegraphs, were impacted because of the currents that were caused by the aurora. The aurora apparently was visible really far at lower latitudes, and that's when you know there's a big storm. The polar regions are generally where the aurora hang out, but when a very strong storm, you can see aurora further at lower latitudes. So it was visible really far south, Mexico, but also there were reports that the aurora was so bright that you could read newspaper at night. I mean, newspaper these days, nobody knows what that is, but the telegraphs actually caught fire because the currents induced in them. So that's how we know it was very strong. That was actually the first time we understood that these flares, it was a very, very bright flare on the sun, had anything to do with what's happening at the Earth. So it was a very important event. There are estimates that could cause, $1 trillion worth of damage now if one of those hits. But again, we don't know when the next big event will happen. That one that I showed you that hit Stereo A was a pretty decent size event. But the Earth is only part of the whole entire circle, so they don't always hit Earth. Other questions?
So I was just wondering what the benefit of an in situ measurement versus a spectroscopic measurement would be. Like, why do you have to get a satellite so close to the sun?
Yeah, Yeah, I mean, that's actually a really good question, because we can get a lot of information with spectrographic data. But I think if you're actually sampling it right there, you can't really do, you can do spectrographic studies on near close to the sun, right? You can look at different features. And so if you're away from the sun in the corona, I think you have to be kind of right there in order to actually sample it. And maybe I'm wrong about that. But I think that you need to be there. I mean, the corona is part. Yes. Yes. So what we're doing is we're not like reaching out and grabbing it, but we have instrumentation that are measuring electric fields, magnetic fields right there, and also velocity and temperature and composition of the plasma. And so when you're looking at white light data away from the sun, you have to kind of be there to do that. We do that near the Earth. So we sample the plasma that's near the Earth. But again, it's not in that inner part of the corona. And to connect it is important. And we don't even know exactly which places will connect all the way back. So that's why it's important also is to get that connection. If you can say, okay, here's an event that we saw happen on the surface through EUV data, and we have solar probe that's sampling how it's impacting the coronal plasma and magnetic fields there, and we have something at Earth or solar orbiter, then again, it's making that connection that's also extremely important.
And if I can add one thing too, it's a bit like if you were to observe a Ferrari at 60 miles an hour and a Prius at 60 miles an hour, you probably think they're pretty much the same car, right? Because you're just measuring their speed, but you don't know how they got up to that speed, whether it took an hour in the case of the Prius, or whether it took a few seconds in the case of the Ferrari. So being at the place where they're hitting the gas is a really important thing to put that whole big picture together.
Can you, what are your thoughts on using solar energy as a method of propulsion, so like a solar sail? And then kind of on that note, what are your thoughts about things like a Geiger sphere?
I'm sorry, say that last thing again?
What are your thoughts about like the Geiger sphere concept?
Geiger sphere?
Or the Geiger sphere, the Dyson sphere, thank you.
Oh, the Dyson sphere. I've heard of that, but I can't remember exactly what it is. So. Oh, okay, I've heard of it.
Or like a very close to the sun solar farm concept.
Okay, that I'm not sure because I've never thought about that.
Okay.
So
well, what do you think about solar sails?
So solar sails, I mean, it's a fantastic.
That's probably more scientific based, I'm sorry.
That's okay. I mean, I had heard the terminology, so I'm like, it must be something. But solar sails, I think it's a great technology, except that it's very difficult to implement, right? Because they depend on the radiation pressure from the sun, which is, you need a very, very, very super thin layer for it to actually impact. And so you need these huge, like massive sails for that to work. Now, I don't know, and we were probably advancing and getting better at utilizing that. So I think if we can really capture that, it'd be fantastic. And I think David probably knows more about that than.
I've designed a bunch of missions assuming that you could use these sails.
Are we getting closer to?
Well, no, so there is this breakthrough prize where they're actually trying to fly a chip-sized satellite camera to Alpha Centauri using a laser-powered light sail, and the light sail is going to be this size. That's the sort of thing you can do if you're a Russian billionaire. There's a lot of stuff going on in that. But there's some advantages to solar sails because they essentially counteract gravity, so you can get out of the ecliptic more easily. You can park in your orbit. If you get a really good sail, you can actually sit there and you don't have to go in orbit to stay at a given distance from the star. There's a lot of advantages, but Holly hit the nail on the head in terms of if you need something the size of a football field and you have to pack it into a box that's this size, the static cling is pretty strong. And so there's a lot of really interesting technologies that come about just to make it work. And so there's been some interesting improvements. We actually got a student here, a postdoc, working on a rebar graphene version of a sail. And that's another, we can talk about that at some other point. There's a lot of work at NASA in space propulsion, mostly focused on solar electric and perhaps nuclear propulsion, because we have very poor solutions for moving around in space. And we know how we get, I mean, we're very inefficient at getting up, it's just chemical, but that's a whole bunch of other things. And as soon as you get to about, if I'm remembering my numbers right, if you get to Mars, then the sunlight is dropping off so fast that a solar sail is pretty much useless once you get beyond the orbit of Mars. So it's got some limited applications.
Yeah.
Sorry for jumping on you.
No, I'm glad you. I see what you did there.
I had a question sort of from a layman's standpoint. When I saw the picture of the sun and the magnetic field, the dark and the light spots, it didn't seem to have any order to it at all.
Yeah.
Versus when you show the picture of the Earth, you have this conical shape to it.
Yeah.
So from a layman's standpoint, am I missing something here? Is the sun the source of what's creating the order around the Earth, and there is no order around the sun?
You're very close. I mean, yeah, that's actually, it's a very good question. The sun's magnetic field is not as simple as the one on the Earth. The one at the Earth is more like a dipole, you know, and so that's a lot easier to study in a lot of ways. The sun is constantly it's changing basically its magnetic field. So during solar maximum, you're going to have a lot of different places where you have little bipoles and a lot of different polar regions. So it's multipolar. It's not that nice dipole structure during solar maximum. And so that was an image during solar maximum. And there's not really an order, except for we know that they have these bands, and that has to do with the way that the sun rotates and how the magnetic fields are structured. So that's something that we would love to be able to predict and understand more. So yes, the sun is it's not very ordered when it comes to the magnetic field lines, but the Earth is much more so. And the Earth is a solid object, except for the very core. So it's you know, the Earth's magnetic field doesn't change and doesn't get as twisted around. I mean, of course, it changes on a very slow time scale, but the sun is twisting around and it's not solid, and it has different velocities depending on where you're at inside the sun and on the surface. So the magnetic field is constantly getting twisted around and changing. Getting good exercise.
So you showed a short video of a coronal mass ejection hitting stereo A, and a few seconds in there was quite a lot of static.
Yeah.
Yeah, those are highly energized electrons, right?
Yes.
Has the video been analyzed at all to try and understand how they get accelerated to those speeds and what mechanism?
From the actual data, the observational data?
Yeah, sort of, you know, a rough in situ, you know, sort of an in situ measurement of the
No, because
particles.
it's an imaging, oh, you mean from stereo itself? The other, yes, they have had, you know, I wish I should have known more about this, but yeah, they have actually studied the impact itself, and that's how we know that had it hit the Earth, it might have been very geo-effective. And as you probably know, it doesn't mean that even if that event had hit the Earth, even though it was very strong at stereo A, and they did analysis of it, it may not have had the same impact at Earth because it's a complicated magnetic field and all that. So yeah, they did, and I'm sorry, I don't know the actual results of that, but that is the way that they came up with the fact that they know it was a very, very strong storm. So.
Okay.
And now, of course, I mean, stereo B has been a little bit lost for a while, so just not communicated with, so it's not really lost. We kind of know where it is. It's not completely lost. We just don't have communication with it. So we can guess where it is. Hopefully we'll regain it.
Quick question. So in terms of hardening our ground infrastructure, I know it can be very expensive to harden circuits and make it so that they're not as susceptible to EMI issues and things like that. My question is, once we know that a coronal mass ejection is coming, what is a reasonably cost-effective way to protect our grid and some of the hardware here on Earth? What do we do? I mean, we know it's coming,
Right.
but
then
how do we?
Okay.
Yeah.
Yeah, good question. From what I hear, you know, transformers are not just sitting on the shelf, and they're very expensive. And I think there's a lot of work being done now to try to improve that so that it's easier to replace the things that are damaged. Also, I mean, we've been very connected in terms of power grids, so that when one area goes out, the rest of them get affected. And so I think what they're doing is trying to make that less so so that smaller area is affected if the power does go out. So it's certain things like that. It's not necessarily, actually, I think that actually the power companies can do stuff if they know there's a strong storm coming. I don't know exactly what that is, but they can do something to help mitigate the effects. But you know, in a longer term view, they're trying to improve the infrastructure so that it's not as susceptible to one transformer blowing or a few, instead mitigating the effects of the area of that. So, but that's not my area, so there might be somebody here that knows more about exactly what power companies can do. We have experts at Goddard that do that.
You had slides on the ejecta that used the words density and velocity, which, you know, to me indicates mass, which to me indicates atoms, but I know it's not atoms coming from the sun. So what is in ejecta? What is the actual
Good question.
material?
So by the time you get out to the corona, the plasma is all ionized. So it's a very, very hot gas. They can't keep their electrons, the atoms. And so it's ions and electrons that are in the hot plasma. So the corona, the white light data that you're looking at, we can see that because the electrons scatter light from the photosphere. So they're looking at basically electron density. Now the velocity and the temperature that I showed was not necessarily of ejecta, but it was of the actual coronal structure itself. Because there are flows, even when there's not huge storms going on, there are constant flows of the plasma itself, and even getting a temperature measurement is important. But yes, if we could do that, and that was with an eclipse, but if we could use those techniques out in space and study it all the time, then we would see those ejecta, and then we could really understand that better too.
Thank you for coming. It was a really interesting talk. I'm curious, as the sun ages over the next millions and billions of years, do you think it'll get more violent, more active as it expands over time?
Not for a long, long period of time. I think not until it gets to the point probably where it's going to become a red giant. Then things change drastically. But in terms of like space weather and coronal mass ejections and flares, I don't think that it's expected to change. Is that right, David? I mean, I haven't heard that.
The activity, I mean, this last maximum was pretty small.
Yeah.
And there's some suggestion
Well,
that there's a couple of 100-year cycle, and there's a suggestion that there may be a 150,000-year
Yeah.
cycle. We just don't know all of that yet.
Yeah.
We had that Maunder minimum, of course, in the 1645 to 1715.
Yeah.
That's not really time, that's actually years. So there's some stuff about these longer-term cycles that we don't fully understand yet. There's some signs in the ice cores and so on. And what that means for the future with it.
Right.
Right. So we don't know if the next cycle is going to be really big or small. Or
This
we're
one
in
could
a
be small.
threat.
But there's no reason to expect the sun to behave that much differently until, of course, it starts doing this weird stuff with red giant. And then even then, I don't know what space weather would look like. I mean, but yeah, I think in terms of
unless it somehow gets into this thing, it's that dynamo action switch.
that's true, and that's
That's where the larger scale cycles come in.
yeah.
It's easy to stop a clock. It's hard to get it started again, especially if it's a clock the size of the sun. And so when it does do this, and it comes out of it, that's a real puzzle.
Yeah.
And some people think it's chaotic theory and stuff that comes in, and there's some information in there, even though it's quiet, and then it suddenly takes off.
Yeah.
But I don't think we understand that.
And the predictions for the next.
Take a big hole and
I don't think that's going to say it. The prediction, it's funny because the last solar minimum that we just came out of a while back, it lasted a really long time, and it was very low, meaning it was even less active than other previous solar minima. And as Dave mentioned, there's another larger cycle that happens, not just the 11-year. But a lot of people model these things, and the predictions were pretty much everything. I mean, we've charted everybody's prediction on how many sunspots were going to happen during the particular solar cycle, and I mean, the graph was just everywhere. I mean, it just was like somebody was going to win the bet because there was everything was chosen in terms of number of sunspots. So we really don't know at this point.
Thinking of digging big holes, this question may be more appropriate for a geophysicist than a heliophysicist. But it has occurred to me, I read somewhere that they have records that the magnetic poles on the Earth have flipped from time to time. And this sort of implies that the magnetic field passes through zero, which means no protection for the planet. And I'm wondering if you'd comment on that phenomenon.
Sure,
How often it is.
So when you said the magnetic field on the Earth changes from time to time, it's actually extremely long time scales. It's like 150,000 years. So yeah, so the poles do change on the Earth as well. But again, it's a very slow process, and it's a more simple field. Now, in terms of the changing the magnetosphere, it does change a little bit of the magnetosphere, because as it's flipping, what happens is instead of the larger simple dipole, you have little magnetic field lines everywhere, right? And so they're kind of changing similar to the sun, but again, on very long time scales. And so I don't think it actually, I mean, it doesn't, there's not really such a thing as it happening where it's zero. But the magnetic field itself does change its shape, and it does expose us to a little bit more, especially of cosmic rays. So right now, I mean, there have been stories about, oh my gosh, it's going to flip, we're all going to die. Well, no, I mean, it's been doing this for a long, long time. And we're in our lifetime, we're not going to notice any difference. So it does change a little bit our susceptibility to solar storms and cosmic rays and things, but not dramatically. I think, I mean, that's what I've heard. So.
Hello, thank you so much for your talk. I don't know too much about this, but you did a really good job at making it interesting and understandable to a layperson perspective. So I'm kind of walking out of here having learned a lot, but also kind of understanding the bad things that could happen, that do happen with these sunstorms and this extreme weather. From a layperson's perspective, are there good things? Is there a good connotation to cast on this, such as reasons why we need these things, or bad things that would happen if we didn't have them?
Well, so again, going back to the longer cycles, so when there's not very much activity on the sun, I always hate saying this because this is not a climate science statement, but the Earth's global average temperature does decrease a little bit. And so, so it does have an impact on the overall global average temperature. Again, it does change, but not the same rate that things are changing now. So in that respect, yeah, I mean, if we don't want to necessarily go through another ice age, but during the period of time that David mentioned where it was called a Maunder minimum, where there were very few sunspots over, I think, 50 years, it was really, really very low activity. And that was when we had a little mini ice age. So for those reasons, I personally don't like cold weather. So, I mean, I would prefer the sun kind of continue doing what it's doing. But I would say in kind of a more philosophical way, if this wasn't happening and we weren't nervous about our satellites, and astronauts are also impacted because they're outside of this protective bubble, right? I would say that we wouldn't be making as much progress scientifically. And so kind of putting a positive spin on it that way is like, this is allowing and pushing us to learn more about these things. And so again, from a scientist's point of view, I think that's a good thing. It's not all doomsday, but and there's a movie coming out. There's a movie coming out called Geostorm, and it looks highly suspect. Don't believe it.
If you don't mind me following up on that a little bit, I mean, when you look at the sky at night and you look at stars, you see a little white dot. If you go to a big telescope and you look at that same little white dot, you see a little white dot. You just don't see as much of the sky. And what Holly has just shown you is a star. And we see a star in close-up. We see it in space. We see we can resolve things. You could resolve Hobby in Bush Airport if you were 93 million miles away looking back at the Earth. You can resolve it in time. You see all these dynamic events. And you can resolve it in energy. You see all these different temperatures. So we actually can study a star in great detail by doing this. And so we learn a lot about other stars, how astronomers, astrophysicists think the sun is really boring because it's too hard for them to understand. But they think it's really boring because as a star goes, the sun is not an exciting, it's not a black hole, it's not a red giant, it's not doing fancy stuff. But there's a great quote from a friend of mine who basically says, the sun is the only star we know of that grows vegetables.
I gotta go see David.
And that's, I mean, that's a glib little phrase, but right? We're the vegetables, by the way, in case you didn't work that out. We're finding stars. So understanding how a star interacts with a planet as we're finding planets around other stars is really, really important. Is there life? Can these planets support life? Well, it depends on what Holly's finding out and her team are finding out about how the sun interacts with planets. And so that's a big positive scientific thing. We're all going to die is the thing that gets us the funding to do this. So we're all going to die. Please call your congressman and tell them to support heliophysics and NASA. Can I ask you just to unless there's another question from you, did you have one, Pamela? You're, okay. So there's a question, somebody's pointing at somebody who, oh, there you go. Sorry, thank you. You just get saved from my Mars question.
Okay.
I never ask questions, but I am so amazed that you mentioned 1645 and thinking about all the dynamics of what the sun is, which it was the sun hero, which mythologically became the source of power from another world for all of the myths forever. But Shakespeare wrote King Lear, his greatest tragedy, in the early 17th century, and you mentioned 1645. There must have been something going on, because in all the paperwork, it is as if there is this sense of tumult, and the writer, Shakespeare, and other people could feel it there, going on through that period of actual tumult, insofar as the wars in Scotland and in other places. And I'm just, for me, the sun and whatever chaos it creates is part of an everlasting world. And I love NASA, and we're always learning. But would you say that what was going on there in the early 17th century, and what you mentioned, was something that actually people at that time could feel, and so the eclipse would be something they could see? But there must have been some sort of force that they could feel. Do you have any feelings about that? What the dynamic of what you're speaking of can actually be felt by a whole culture long before we had the technology which you're using?
So I would say physically, no, because these things actually don't impact us here on the surface. But if there are things changing on the Earth in general, again, philosophically, when things happen in the sky that we don't fully understand, I think that collectively can cause some feelings of something. And maybe it could be a religious sort of feeling, or just knowing that we're connected somehow with the universe. So I would say not from a practical sort of physical standpoint that people could feel anything different, but I think knowing how history has developed in terms of scientific progress, I mean, I think that's a pretty cool thing. And I could see people feeling something from that. But that's more of a kind of an emotional, philosophical answer, but I don't know if that answers the question. It's kind of a difficult question. But okay.
Well, it was pretty cold, so that
It was
might,
cold, so
might explain why the
there's
Scots tried to move south. And anyway, I think that's been obviously a great talk, a great response again from our audience and stuff. So please join me in thanking Holly again.